Okay, we left off at question 8.37D. We're starting here with a tertiary alcohol, and we want to make this alcohol here where the hydroxyl is going down and the methyl group is pointing up. Well, in terms of retrosynthesis, we use a retrosynthesis arrow. That's what this arrow is. It means retrosynthesis. If we could make this alkene, 1-methylcyclohexene, right, then all we'd have to do is an anti-Markovnikov addition of water across that double bond, because anti-Markovnikov addition is syn addition, and the hydrogen and the hydroxyl end up on the same face of the molecule, and the hydroxyl is going to end up on the carbon that's richer in hydrogens. So then the question becomes, how do I go from here to here? Well, this is one of those cases where we can use my favorite reaction, one of my favorite reactions, which is where we simply take this molecule and we heat it up with concentrated sulfuric acid. Just heat it up, and you're always going to end up with the most substituted alkene, which would be the Zaitsev alkene. So there we go. Now all we've got to do is take this and treat it with borane and THF in the first step, and then in the second step we'll treat it with hydrogen peroxide and sodium hydroxide, because we want to do an anti-Markovnikov addition of water across that double bond, which again is syn addition. Okay, let's take a look at question 8.39. Question 8.39, I'll move down here. Plenty of space. So this is question 8.39, and we'll start with part A. And again, it's just identify the reagents. These are great practice problems. We're starting with this compound. This is called methylene cyclohexane. And we're going to make 1-methylcyclohexene. Okay, so I'm basically moving the double bond from outside of the ring to inside of the ring. Well, I know that based off of what we saw in the last problem, that in terms of retrosynthesis, if I could have this tertiary alcohol, right, all I would have to do is heat it with concentrated sulfuric acid, and I'd end up with the Zaitsev alkene. And so then the question becomes, well, how do I get from here to here? Could anybody suggest how to get from this alkene to this tertiary alcohol, and it's not a trick question? Could anybody make a suggestion as to how to do this transformation, to go from the exocyclic alkene to the tertiary alcohol? It's a Markovnikov addition of water, and there's no carbocation rearrangement to consider. Doesn't happen. So the best way to do that would be to treat the molecule, exactly, thanks Mackenzie, would be to treat the molecule with just aqueous acid. That's going to give us the tertiary alcohol that we want, and then all we have to do is blast that with concentrated sulfuric acid. So we'll put sulfuric acid that's concentrated, heat it up, and there we go. We're going to end up with the Zaitsev alkene. Is there another way to do this reaction? I'd say yeah, there's another way to do this reaction. Let me show you. Another option would be to take my starting material and just to treat it with HBr. That's going to do a Markovnikov addition of HBr across the double bond, and that's going to give me this compound. And then all I have to do is treat that with sodium methoxide, right, which is going to give me the Zaitsev alkene as well, and that would give me my desired product too. So either way works. They're both two-step syntheses. So both syntheses are 2 steps. So either way works. Let's try 8.39b, and we're going to take a look at C and D as well. So this is 8.39b. And we have this compound here where we have the double bond here and we want to take this compound and we want to put the double bond in here. So we want to go from a Hoffman alkene to a Zaitsev alkene. Well, to do that, all I need to do is a Markov-Nikov addition of HBr, because that would give me this tertiary alkyl bromide with the bromine here. And then if I want to pull off this proton that I'm writing out in red, that's the least hindered beta proton, because I also have these beta protons here. But if I use sodium methoxide, right, that's going to give me the Zaitsev alkene. Now the question also asks us, how would we get from here to here? Well, the same type of thing. I mean, in the first step, you could just add HBr to it, and you'd end up with the same, you'd still end up with this intermediate right here. But then to make the Hoffman alkene, you would treat it with potassium T-butoxide to pull off the less hindered proton. So you can see you can go back and forth between these two alkenes. Let's see, 8.39C, we have this compound. So this would be what, 2-methyl-1-butene. And we want to make this compound, which would be 3-methyl-1-butene. So we want to move that double bond around. This is going to require a little more work, won't it? Right? Because in order to make this compound, in terms of my retrosynthesis, I need to have this alkyl halide, and then I could just treat it with potassium T-butoxide, right, to produce the Hoffman alkene. So then how do I get from here to here, right? I need to move the bromine, to this carbon, to this carbon right here. I need to put my bromine here, right? If I just do a Markov-Nikov addition of HBr, that's not going to put the bromine in the right spot, is it? That would give me this compound where the bromine is here. But then I could take this molecule and I could treat it with sodium methoxide, and that would give me the Zaitsev alkene, but it would give me this Zaitsev alkene. Is there a way to get from here to here directly? Absolutely there is. All right, all I have to do is an anti-Markov-Nikov addition of HBr. So I use hydrogen peroxide, or sorry, an organic peroxide, and I'd end up with this compound. And then to get from here to here, I just treat that with my potassium T-butoxide, like that. Well, let's look at one more. So we'll do one more, and this is 8.39, question D. We're starting with our favorite exocyclic alkene here, and we want to make this compound. And again, there's probably more than one way to do these. But again, in order to make this compound, I'm going to have to have this where I've got, this compound where I have this bromine, right? Because then I have beta protons. I have a beta proton here, but I also have this beta proton here. And so in order to pull off the beta proton in blue, I'd use a hindered base to give me what would be the Hoffman alkene. So then the question becomes, well, how do I get from here to here, right? If I take this alkene and I treat it with HBr, okay, that's going to give me a Markov-Nikov addition, which puts my bromine here, but the bromine is not in the right place. So if I treat this with sodium methoxide, or sodium ethoxide, doesn't matter, I would end up making the Hoffman alkene from this alkyl bromide, and then I can treat that with HBr and an organic peroxide to give me this compound where I have the bromine here now. And now I can treat that with potassium T-butoxide, and that will eliminate the beta proton that I had written in blue all along, right? Your T-butoxide is going to pluck this proton off, produce the double bond, loss of leaving group, like that. There we go. So that covers all of the practice problems that I had in the slides and all of the reactions for this chapter.